Okay, we're recording. So, yeah, last time, here's what we were talking about. We were talking about change of variables in 3 dimensions. So keep in mind, it's just like change of variables in 2 dimensions, right? So the big idea is that if there is a function pushing forward that turns a nice domain into an undesirable domain, then an integral on the undesirable domain can pull back to an integral on the pullback, what you might call the original, right? But the new pullback domain on the left. Okay, so pullbacks go the opposite direction, and stretching factors. Let's see here, colors. Stretching factors account for the fact that these are in fact different domains or different sizes, and you have to account for that in all of the arithmetic. Okay, so same basic idea as in 2 dimensions, and we talked about this preliminary theorem. Let me go ahead and talk about this theorem again. We've already seen an example of this. That if you have a linear transformation represented by a matrix, then the derivative of that linear transformation is the same matrix. Now, it looks weird, looks a little surprising. How could it work out that nicely? Give it a try. Just write down, let's say, a 2 by 2 matrix. You'll notice the pattern pretty quickly. You can just write down any 2 by 2 matrix, multiply it out to find the formula for the corresponding linear transformation, compute the derivative matrix of it. You will get the original matrix back. It's almost like a little magic trick. Okay, so with that in mind, here's the 3-dimensional example I'm going to show you all. This is actually a wonderful example. It's another one where change of variables turns a brutally difficult problem into an easy problem. Okay, so here we go. Our domain for this is going to be this parallelepiped right here. Defined by 3 given edge vectors. And this is a pretty common way to describe a parallelepiped. We just described the 3 edge vectors, and the parallelepiped sort of follows from that. Now, before we get into the change of variables, just to appreciate how much we need help on this, let's zoom in and think about how would I slice this up, just for the I don't know, the nasty thrill of it all, right? Just to see how bad this is. When you start slicing, let's say perpendicular to the y-axis, and forgive my art on this is going to be hard to draw. I think slices perpendicular to the y-axis will kind of start off looking like little triangles, kind of like that, right? And then eventually, though, you're going to hit this corner, at which point the shape of the cross-section changes. And then, not long after that, you're going to hit this corner. And then not long after that, you're going to hit this corner. And then after that, this one, and then this one, and then this one, or probably that one somewhere in between. Oh my gosh. Right? You're going to be hitting corners all over the place. And let's further recognize that on each one of these slices, the slices are not always triangles like this. Some of the slices, okay, artistic challenge here. Some of the slices are weird polygons like this and have multiple sides, which means that as you're slicing up one of these, right, as you're slicing up that, let's say perpendicular to the z-axis, well, then you're, where's my button? Here we go. You're going to be hitting the various corners as you go up slicing that. So you're going to have 6 interior corners as you slice in the outside direction, which means 7 integrals to start. But then on each of those slices, you're going to have multiple, possibly several integrals on each of those slices because of those corners. So this is probably, I've never counted exactly, but this would be somewhere in the ballpark of like 20 or 30 separate integrals. This is brutally inconvenient. Okay. All right, so how can we avoid all of that terrible, terrible ugliness? Here's the trick. This is super clever. This is not a follow-your-nose observation. This is a really insightful trick is really the wrong word. Trick makes it sound trivial, like this is just silly business, right? No, this is a insightful, brilliant idea that someone thought of. And it wasn't me. Somebody showed me. The big idea is as follows. These edge vectors that define your parallelepiped, make those the columns of a matrix which you can then use to define a linear transformation, and that should be your change of variables function. It's as simple as that. Take the given edge vectors, make those the columns of your matrix. Now let's see why that's such a great idea. What is so convenient about making that choice? What's great about this is, let's look over here at the unit cube for no apparent reason. Certainly, if this was our pullback domain, we'd be happy, right? I'd much rather do an integral over a three-dimensional cube, unit cube no less, 0 to 1, 0 to 1, 0 to 1. Again, everybody's favorite domain for a triple integral. Constant, easy bounds. You can't beat it. What is the image of that by way of this linear transformation that we just defined? Right? Well, the way we're going to understand the image is by looking at, well, the edge vectors. And the edge vectors over here on this unit cube are standard basis vectors. I'm highlighting there E1, the first edge vector, first standard basis vector. And what happens when you plug that into your linear transformation is you get as your image the first column. That's how, linear algebra works. Again, one of the most important facts to know about linear algebra is that matrix times standard basis vector gives you the corresponding column. And of course, we have cleverly arranged for that first column to be our first edge vector, name of the first edge vector over here. So this is the beautiful little arrangement. Because of our clever choices, an edge of the unit cube goes to an edge of our parallelepiped. And likewise for the other edges of the unit cube, they go to the other edges of the parallelepiped. And then by a linearity argument, the entire unit cube has as its image this entire, all at once, this entire parallelepiped. So just exactly what we need. Keep in mind, that's which, if you want to do a pullback, right? The whole idea is that the output domain needs to be exactly the image of your pullback domain. So we win. It's all over, but the shouting at this point, we had this nightmarish domain over here, on which we're doing some sort of an integral. We pull back, and now we have this wonderful convenient domain over here on which to do our new integral. And it's super duper easy. The only little detail, of course, is we have to think about the stretching factor. Right? The stretching factor, well, it's the absolute value of the Jacobian determinant. You just have to compute the determinant of the derivative matrix. Of course, the derivative matrix is the matrix per this theorem up here, which y'all are going to, again, check on your own just to make sure. You want to see how that algebra works so that you're not just taking stuff on faith, right? This is easily demonstrated. Take the time to see that through for yourself. And so life is good and problem solved. How we doing? Everybody on board? Great trick. So, again, three-dimensional change of variables, pretty much the same as two-dimensional. Okay, that said, we're going to move along now to what I see as a pretty different topic. The book views this as kind of a special case of what we've been talking about, namely change of variables. And I do agree that it is extremely valuable, and I think the ideal way to think about what we're about to do is that it is literally a change of variables. Absolutely. But I feel like we've been in section 5.5 now for quite a while. I feel like this deserves being in a new section. But anyway, not that it matters, but anyway. Okay, so we're going to talk about what it means to do an integral in a coordinate system. This is a brand new concept. Every integral we've done so far has been what we'll call a rectangular integral. dx, dy, dz, and related. Okay. So the foot in the door on this is something we talked about a while ago. You'll recall that when we defined polar coordinates, my primary point of view on polar coordinates was to view it as a function that takes r's and thetas and gives you x's and y's, right? Don't think of this as geometry that happens within the xy plane. Think of this as a function whose target is the xy plane. Is that cool? Is everybody good? Okay. All right. So likewise, cylindrical coordinates is a function from r theta z space into xyz space. And spherical coordinates is a function, right? We've seen these formulas long ago, right? But it's a function from rho phi theta space into xyz space. So we have three different coordinate systems. They are three different functions. And then what's awesome is that not only can you, but very often it is very convenient to use them as change of variables functions. These are fantastic change of variables functions. Highly, regularly, exactly what you need change of variables function. Arguably the most important change of variables functions out there. Debatable, but anyway. So now our usual process on doing change of variables is, first to decide what function to use and only then to compute the stretching factor. After all, you need to know the function before you can crank out the stretching factor. But we're going to be using these so much, we're going to take a slightly different strategy. We're going to write down their stretching factors now and just remember what the result is, and therefore never have to do that computation again when we're using these change of variables functions. So this is just a bit of algebra, and y'all can go through this calculation here for yourselves. It's not hard, right? We have x and y as functions of r and theta. You can compute for yourselves the r partial and the theta partial, make those the columns and the blah, 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 right? It's a whole routine. You do that and take the determinant and all. Your stretching factor is r. Correction. Your Jacobian determinant is r. Now, sadly, your stretching factor is a little bit different. It's very important to recall. The stretching factor is the absolute value, right? So we are going to have to take the absolute value of r. That's a little bit irritating. Nobody likes absolute values. They get in the way in the integral. You have to consider cases. It's annoying, right? But yeah, that's what we have. That's how it turns out. Likewise, healthy exercise. Everybody should do this once in their lives. It's not that bad. Compute the stretching factor for cylindrical coordinates as a change of variables function. And again, you get r. Okay, well, fine. With the absolute values, you get absolute value of r. Okay, lastly, spherical coordinates. And again, everyone should do this once in their lives. And this is, well, I would say not that bad, but it's got several steps in it. This is I'm going to say 5 minutes. All right, there's a little bit of doing that it takes to. But this again is a healthy exercise. Everyone should do this. It's just a bunch of trig. It's good practice in handling large expressions, and you'll notice the value of keeping your work sort of organized and neat so that you can make it easier for you to see algebraic conveniences if your work is clear. So you go through that. By the way, the big trick that makes the algebra on this work out, Pythagorean identities. Y'all remember that from trig class way back when, right? Sine squared plus cosine squared is 1. That comes up like 3 times when you do this calculation. So again, everyone should do that. The answer ends up being rho squared sine phi, and again, don't forget your absolute values. So absolute value of rho squared sine phi. So, cool. Done once, never have to do it again. Just remember those stretching factors for these three different functions. Now, let's address this absolute value business. Again, nobody wants to have to deal with the absolute values. That's bother. That's going to be inside of your integral, right? So here's the solution. We have previously allowed ourselves, because we had no reason to restrict ourselves, we have previously allowed ourselves to use any values of r and theta. Why not? Right? So now, though, we have a motivation to make a different choice. We are now going to restrict our flexibility there. We are now only going to allow positive values of r. Notice this is a choice. We don't have to do this. There is no law that says we must do this. This is just a choice, right? But if we make this choice, if we choose never to pick negative values of r, then, well, now, very conveniently, if r is known to be positive or non-negative, then now my stretching factor, I no longer need to bother with absolute values, and that's a huge win. We've eliminated the absolute values. This is a nice benefit, and it is well worth the cost of having to sacrifice, let's face it, negative values of r. We never liked those in the first place, right? It was always kind of annoying. So, small price to pay. Big benefit of losing the absolute values. So likewise with the cylindrical coordinates, just choose. You don't have to, but you really should choose to always choose positive values of r, non-negative values of r. And so again, the absolute values go away. The common misunderstood one, a lot of students get this wrong. Looking at the stretching factor that we have here, thinking about that, how are we going to get rid of this absolute values? The wrong reasoning that a lot of students speculate is that, well, you know, come on. I mean, rho is kind of like r. Maybe I should just require rho to be positive. What is that bias? Looking at this expression, not a thing, right? Knowing that rho is positive just tells you that the rho squared factor is going to be non-negative. We knew that already anyway. Right? So please don't step on that landmine and think that as long as rho is positive. Not at all. It's got nothing to do with the absolute values. What we need is to find a way to arrange for sine phi to be non-negative. What restriction can we put on ourselves to arrange for sine phi to always be positive? And the way we do that is by choosing always to let phi be between 0 and pi. So that's the move here. It's got nothing to do with rho. Everybody good? All right. Okay. So a couple of little sacrifices, a couple of formulas to make sure you have memorized. And by the way, I emphasize, so important to have these memorized. In some sense, all of the rest of what we're going to be doing is just kind of plugging in pat expressions, right? So the case could easily be made that these stretching factor formulas, I don't want to overstate it and say that it's the only multivariable calculus in this sort of technique, but it's a big part of it. So think of this as easy money. Think of this as if you get the stretching factor right, you've already got several points. It depends on how many points the question's worth and what else is going on, blah, blah, blah. But just knowing your stretching factor and getting that in there. Points. Don't walk away from free points. Okay, so let's see an example. We want to do a integral, it seems here, defined on this domain, the first quadrant portion of the unit disk. Now, if you run at this straight on, head on, blinders and everything, and just start slicing it up, right? And slicing first perpendicular to the x-axis, and your slices look like this. And then you think about the upper bound points, right, are on this curve over here. And if you solve for y as a function of x on that curve, you can see this coming, I'm sure. You're going to have square roots on your inside bounds. And we know we've been down this road. right? And we know what happens here. If you have square roots on your inside bounds, then pretty likely you're going to have square roots in your in your outside integrand, which means this integral is going to be unfriendly. Now it's doable. Trig substitutions. But again, that's, it's a problem. It's annoying. Right? So we don't want to do that if we can possibly avoid it. So we're going to use our brand new shiny tool, namely the polar coordinates change of variables function, right? And the polar coordinates pullback of this undesirable domain that we started with, right? The polar coordinates pullback, I claim, is just a rectangle. And this is a good little geometry exercise to kind of think through. Of course, obviously, rectangles are awesome. We love rectangles. Constant bounds. Hard to beat it. So now how do I know this is true? How do I know this is the pullback? I can just look at the edges one at a time and note that the edges on the left, when you put them through the polar coordinates function, just turn into the edges on the right. So for example, let's look at this edge right here. That edge is where r equals 1. You can see it right here in the picture. R is equal to 1 for this whole edge. We start at theta equals 0. It ends at theta equals pi over 2. And I can tell you exactly what that looks like in the xy plane. It's literally exactly that edge of the undesirable domain that we started with. And then, make your way around and just notice that all of those edges, it just traces out exactly this shape. It's very convenient. Everybody good so far? Oh yeah, question.
Is it acceptable to do you just directly write the double integral is equal to the iterative integral in the other one, or should you do the double integral in R, if R is the quarter circle, equals double integral over, and then assign dash h something, and then say it's the iterated integral?
I'm sorry, I guess I'm just not quite understanding. How about let me make a proposal. How about we'll do a couple and then see if that might inadvertently answer your question. If it doesn't, ask me again. Okay. Is that cool?
Yeah.
Okay. Cool. All right. Okay. So let's walk our way through what we've got now. We know we have a pullback domain. That's going to be the bounds for our new dr d theta integral. Easy bounds because it's a rectangle. And now there's really only two things left. There's, don't forget to plug in, right? X squared plus y squared in polar coordinates is r squared. We got lucky with that one. I mean, usually you'd have to actually plug in x equals r cosine theta, y equals r sine theta, and then, kind of do some algebra and hope you might get lucky with the trig identities or something. Here it would just, again, sometimes it's easy. So that's the first thing to do. That's just plugging in. The last thing to do, and again, easy to mess this up, the last thing to do is to rewrite the area element, the area differential here, dA, right? So how do I represent area in the xy plane, but in polar coordinates? Well, we've already computed our stretching factor. We already know from the previous page our stretching factor is r. Stick it in there. And dx dy just becomes r dr d theta. We're good. Now off to the races. And now instead of having to deal with this highly undesirable single variable calculus nightmare of trig substitutions and stuff like that, much easier to look at this integral. After all, our integrand is just r cubed. Yeah? Integrand's r cubed. The antiderivative is 1/4 r to the 4th. There's nothing to it. Boom. Done. Everybody happy? Real neat move. Okay, so now a quibble could be made here. It's pretty evident here that we have used polar coordinates as a change of variables function, right? But it seems like maybe a bit of an overstatement to say we're doing the integral in polar coordinates, because we literally did it is just a change of variables, right? So what do we mean when we say doing an integral in polar coordinates? That is, in fact, just a streamlining of what we just did. So what we just did was to pull back, look at our new domain in the r theta plane, and then, proceed. And, of course, proceeding means to, slice it up. And these are what theta slices look like. And then on any given theta slice, if I focus on one theta slice in particular, then I can talk about the range of values of r, and r starts there and r ends there. And that's just the usual slice it up process. So the key observation now is to point out that, look, this theta slice, all it is the set of points in the r theta world where theta takes a given fixed value. It's just a fixed value of theta. That's all it is. And I can see that just fine and dandy over here in the xy plane. Right? So now looking back at the example we just did, why did I draw the pullback domain? Why did I have to think through all the edges and stuff to get this? Well, it's so that I could slice it up. All I really need from the pullback domain is to think about how it slices, because how it slices tells me these bounds. So the cool observation I'm making down here is that, this process of slicing that you do in the r theta world, you could totally do that in xy world itself just by knowing what the slices look like. And this is what theta slices look like right here. Right, they're just little rays kind of emanating out of the origin, and etc. So now I am going to revisit the example we already did. Same example. This time, though, while I doff the cap to, yes, in fact, this is a change of variables function, and yes, there is a pullback domain over here, and yes, that pullback domain is what I'm slicing up, but I don't need to look at the picture over there. My slices, a slice over here in the theta direction, those are just slices like this. That's a theta slice, as seen in XY world. So, I'm doing a pullback, but I don't need to draw that. I don't even need to think about that particularly. Everything I need from the pullback I can see right here. So, specifically, let's get some details down. I can talk about theta starting at 0. Okay. There's theta equals 0 right there. You can see it right here in XY world. I can imagine several other slices happening in the middle. Okay, yeah, cool, fine. Here's several other slices along the way. And then I can see my last slice where theta is clearly pi over 2. Okay, yeah, right. I can see that too, right over here. That's pretty cool. You don't even have to draw the pullback. So that makes life a little bit easier. You can just kind of go straight at it without drawing the pullback at all. Yeah, question?
Sorry, I'm kind of confused by when we're pulling back dA and then we make it r, dr, d theta.
Yep.
Why is there an r in that?
Yeah. So that's our stretching factor. So remember, whenever you do a change of variables, right? Whenever you do a change of variables from dx dy to d whatever, du dv, whatever it is, there's always a stretching factor, and we already computed it. Yeah, is that cool?
Yes.
Yeah, right. Okay, so here's another example. Now this one, I'm not going to do the old-fashioned way first. I'm just going to remove the net, right? We're going to free climb this integral. We're going to do this, as they say, in polar coordinates. And keep in mind, yeah, sure, it's a change of variables. Yeah, it's a pullback. Yeah, there's a pullback domain. Okay, but we don't need to draw that. We're going to see everything we need to see right here in XY world as we do this example. And here's what my slices look like. Let's see here. If my domain is the unit disk, like so. All right, well, I'm going to imagine slicing it up as follows. I'm going to start with this value of theta. Theta equals 0. And then I'm going to imagine sort of going all the way around. Right? There's a lot more slices, a lot more theta slices as I go around the disk. And then I'm just going to end. Let's see, I'll do green. I'll end when I finish tracing out my domain. We end at theta equals 2 pi. Right? So the range of values of theta, you can see right here in the picture, 0 to 2 pi. Is that all right? You can also see, and this is a good thing to notice, we're responsible for, for any given fixed slice, in other words, now for any given value of theta, we've got to think about what's the range of values of our next variable being r. So where does r start on that theta slice? Well, no problem. It starts right there, where r is clearly 0. Right? And where does r end on this theta slice? Well, it ends at that point, which is on this curve, which has equation r equals 1 because it's the unit, it's the boundary of the unit disk. And what is the value of r on the curve r equals 1? Well, it's 1. And we're done. No pullback. Needs to be drawn. Okay, we're going to do several more examples here. I do want to give you some tips and tricks before we proceed along. You do technically have two choices, of course, in which way to slice. You could do dr d theta or d theta dr. As it turns out, vast majority of cases, in my experience anyway, and I think this is pretty clear, vast majority of cases, you want to do the r on the inside, theta on the outside. For one thing, if you imagine some algebraic relationship between r and theta, typically we like to solve for r. Like we've seen a bunch of polar curves like r equals sine theta. R is clearly more naturally a function of theta than the other way. If I put theta on the inside, I'd have to say theta is like arc sine, and then you'd have to worry about cases. Well, wait a minute, for which, you can get in real weird places if you introduce inverse trig functions. So vast majority of cases are on the inside. Next little tip, I think this is a big one. This is arguably the biggest one. Always write this expression here down all at once. Please do. You don't have to technically, but I urge you, it's very much in your best interest to always write down r dr d theta all at once. The reason why is if you just write down just dr d theta first, and then you come up and you start thinking about theta slices and what's the range, and then where does r start, where does r end, and you're lost in the geometry of all of that, you can forget to stick the stretching factor of r in there. Now, of course, as we've discussed, that's really important. That stretching factor r is a significant amount of the multivariable calculus aspect of these questions, right? I don't want to say it's the only thing, but it's really important. It's 3 points. Don't put yourself in a situation where you might accidentally forget. To put it in there. I've seen it happen a million times. Like 20% of the students will forget to put the R in there if they don't follow this rule. So again, there's no reason not to. Right? There's no circumstance in doing in actually working out the algebra of a question. There's no circumstance where you will not need that R. You will never write down dr d theta without needing the R next to it. There's no reason not to write it down all at once. So again, I implore, please write that down all at once so you don't forget it. And then of course, the way we find bounds is the usual. We identify key points. We identify what curves or surfaces they're on. We identify the corresponding equations. We solve for what we need. Okay, so just a bunch more examples now. This is a nasty one here. Surprisingly nasty. Our domain here is this annulus, kind of a ring sort of a thing. In my mind, I don't know why, I see a moat around a castle. That's just how my head works, I guess. I don't know. And if that is our domain, let's first eliminate a couple of clever ideas that we might be tempted to try to follow. So the first clever idea we might try to follow would be to compute the integral on this whole disk and then subtract the integral on this sort of inside disk. Right there, right? So green minus blue, right? Clever move. You compute the green integral, which is easy. You compute the blue integral, which is easy, and life is good. And this is nonsense. It's nonsense because if you look at your integrand here, right, your integrand is undefined at the origin. We do not play with undefined. Right? If you want to invoke the fundamental theorem of calculus, one of the little asterisk, one of the conditions on that is the function has to be continuous throughout the whole thing. And undefined is not allowed for continuous. Right? So there is no integral to compute here. The integral over d2 is undefined. That's a bunch of nonsensical garbage. You may be thinking to yourself, well, yeah, but I could compute an improper integral. Improper integrals with multivariable that's not analogous to single variable. It's weird and dangerous, and we're not even going to talk about it in this course, right? So you cannot define that integral or that integral. Just makes no sense at all. Okay. Here's the next approach we could take. We could just do the rectangular approach, but the problem is you'd have to do that piece separately. You'd have to do that piece separately. You'd have to do that piece separately, and you'd have to do that piece. If you want to do this in rectangular coordinates, you've got yourself 4 integrals, on all of which, notice, your bounds are going to be on circles, which in rectangular coordinates will give you square roots. So you have 4 hard integrals. We don't want to do that. So, let's do it in polar, and it's falling down simple. It's just easy. Our theta slicing, right? Theta kind of goes all the way around like this, starting there, where theta is equal to 0, and ending sort of there, where theta is equal to 2 pi. It goes all the way around, in other words. So 0 to 2 pi, boom, cool. We're halfway there with an easy geometric observation. And then, now looking at a fixed theta slice, let's see here. You know what? I'll use blue for this. Looking at a fixed value of theta, R starts at that point, which is on that curve, which has this equation, in which I solve for R to get that, right? And then it ends at this point, which is on that curve, which has that equation in which I solve for R to get that. And we're done. Boom. Easy. Nothing to it. Way better than those other options. A quick reminder, don't forget, and notice I did this. I guess I can't prove that I did this as I wrote this down, but I promise I did. When I wrote this down, I did not write dr d theta. I wrote down r dr d theta as my little sort of, it's my little psychological trick to defend myself against my own absent-mindedness, right? And you may think you're not subject to such concerns, right? But again, my experience is a lot of students. It amazes me every semester how many students will just straight up full on forget to put that in there, and I can't give the points if I can't. I mean, I've got to award points based on what's written on the page. So Don't forget that stretching factor. Okay, let's see here. Next example. This is a little bit harder one, a little bit weirder. Our domain is this shape here, kind of a sort of a crescent moon-ish sort of shape, right? Notice that what it says here, just looking at it literally, this is a disk. Right, we're looking at what's inside of that disk. But specifically, we are looking for the part that is outside of that disk. So purple, but lop off all the blue. And that gives us this gray shaded region right here. Okay, so that crescent moon being our domain, how do we slice this up? Now again, you could do this in rectangular coordinates. Again, that's kind of a nightmare. You get that chunk, you get this chunk, and you get this chunk, 3 separate chunks. Nobody wants that. Right? So instead, we just have to think through the slicing. Theta slices are going to kind of look sort of about like this. All right, we got to think about first and last. Okay, so let's start with our last. Our last theta slice is going to be right there. Now, there's a couple different ways to proceed to understand that point. You can, it's perfectly fine, you can view that as, well, look, that's on this curve with that equation, and it is on this curve with that equation, and you could then solve for theta in that algebra. It's not even that bad, right? It's fine, yes.
Was the r equals 2 cosine theta given to us?
No, that's not. No, so that's something you have to do by first writing down the rectangular equation for this circle, and then going through that conversion process. Yeah, so that's a great question. That's one of the reasons why we actually bothered to talk about how to convert equations from rectangular to polars for just such an occasion. Yeah, right. Yeah.
Could you just walk through how you got the pi over 3 and negative pi over 3 balance?
Yeah, that's what I'm working on right now. Yeah. Okay, so again, one thing you can do is you can understand this point as coming from these two equations and solve for theta, right? But the better way, what I think is easier, cleverer, is to notice that that point is part of an equilateral triangle. Specifically, that length is 1 because it's a radius of that circle, right? And then furthermore, that length is 1 because it's a radius of that same circle. And furthermore, that length is 1 because it's a radius of that circle. And that makes this on the inside then, this is an equilateral triangle, and we already understand a lot of stuff about equilateral triangles. In particular, the relevant angle is just one of those triangular angles. Yeah. So this, it follows, is pi over 3. Is that cool? Right, and then, by the way, analogously, this, of course, is backwards. Same argument, really. Analogous argument, anyway. And so that's negative pi over 3. Is that cool? Okay. Okay. Let's see now. What about the bounds on R? Well, again, as usual, we have to look at our theta slice. There's a theta slice. The starting point is going to come from there. By the way, thank you, picture. Right? The picture tells us that on a theta slice, R starts at that point, from the picture of which I see that it comes from that curve that has that equation, and that's how I get that lower bound. And then likewise, my R slices, my R values on my theta slice end at that point, which is on this curve with that equation, and that's where that upper bound comes from. Cool? Right. Don't forget. Easy to forget, right? It's so easy to forget because we've streamlined it, right? Because we've already, it's like I didn't even have to compute it. And somehow something about the way the brain works, if you don't have to earn it, that it's easy to kind of ignore it, right? So don't get stung from the fact that we've streamlined this process and the stretching factor is already established. You have to put that in there. I cannot emphasize that enough. Okay, right. So next example. This one is really cool. It is what I'm going to call historically interesting. This is a calculation that goes back hundreds of years. It is also important because of the fact that this integral comes up a lot. Now, if you are curious where this integral comes up a lot, it has to do with statistics. And you all may have seen, depending on whether how much stat you've seen, this thing called a normal distribution, and that's what this curve is. It's something called a normal distribution. It's one of the most commonly occurring statistical distributions in nature. It's a big deal, right? And it's not just in nature. It's also just in, as it turns out, there's a big theorem in statistics that if you have any shape of distribution, and if you sample from that distribution a bunch of times, and look not at the individual values, but at the averages of those values, the averages will have their own distribution. And as n approaches infinity, it will always approach this. So this is really naturally, not just biologically, but mathematically naturally important distribution. And so knowing the integral is kind of a big deal. And again, y'all will recognize we don't know how to do antiderivatives of this. So this is very important and very hard. And the following calculation, really cool. This is a slick move. This is one of the cutest tricks that I've seen in analysis. I absolutely did not think of this on my own, and I doubt I ever would have. But here's the slick move. What you do is you take this integral, you give it a name, you call it J, arbitrarily. You multiply it by itself for no particular reason that's apparent yet. Now, let me point out, a lot of people would complain, wait a minute, these don't look the same. This has got X's in it, this has got Y's in it. No fair, they're not equal. Don't forget, X and Y here are just dummy variables. These are truly the same integral. It's just kind of the alphabet is the only thing that distinguishes these integrals from each other. They are truly the same value. Dummy variables don't matter in the evaluation. So that is, in fact, J squared. Then the next slick move is to point out that for the purposes of this y integral, I can treat this as a constant. I mean, it literally is this is some number. I don't know what that number is yet, but it's just a number. So as far as y is concerned, that's a constant. I can just whip it right inside of the y integral like so. Perfectly legal. And then I can look at this x integral. Note that's the inside integral, which means that the outside variable, where's my gray hit? My outside variable, for the purposes of that inside integral, my outside variable is to be viewed as a constant. That means e to the negative y squared is a constant, and that constant can just whip inside of there, like so. It's really clever, right? It almost seems too good to be true that you could just whip things around like this. And yet, notice what we get is now a new integral, a new iterated integral. And pretty quickly, you will notice that this iterated integral covers all values of x and y. Namely, it covers the entirety of the xy plane. And at this point, A lot of students would look at this and say, okay, we've successfully turned a hard problem into an even harder problem. And that's, right, kind of true. This seems worse until you decide to do it in polar coordinates. And in polar coordinates, the stars align. X squared plus y squared is r squared. The bounds on r and theta, sweeping out the entirety of the xy plane, are like so. And don't forget your stretching factor. Again, so easy to forget that stretching factor, but there it is. And now it's an easy integral, because my new r integrand has this extra factor in it, and this works out no problem. Easy calculation. So the final result then is that very important integral that we had no idea how to compute because the antiderivative doesn't exist is square root of pi. So nice way to end it. Y'all have a good rest of your Wednesday. We'll see you later.